Welcome to this webinar on motor cooling system design with Motorcad, Simulink, and Simscape, brought to you by MathWorks and ANSYS. I'm Angel, an engineer from the Simscape electrical team at MathWorks, and I work on modeling and simulation of motor drive systems. Joining me today is Hussein, who is an engineer at ANSYS working on thermal modeling of electric motors.
Hi, Uncle. Thanks for having me today. I'm looking forward to this webinar.
Me too, likewise. Hussein, you have extensive experience in thermal modeling of electric motors. And I wanted to ask you, why is it so important to carefully design your cooling system?
Well, Uncle, designing electric motors is not simply an electromagnetic problem. It's important to consider all aspects of a design. We look at NVH to analyze noise and vibration. We do mechanical stress analysis to ensure the machine has structural integrity. And just as importantly, thermal analysis, which will impact the machine performance and its lifetime. So as the motor operates, heat is generated internally within the windings, within the magnets, within the stator and the rotor, and the effectiveness of the cooling design in extracting that heat and rejecting it from the motor determines the continuous performance of the machine. So there's several reasons why this is the case. Firstly, the resistivity of copper increases with temperature. So as the copper windings get hotter, their resistance increases, and this leads to increased resistive losses within the windings, which then reduces the machine efficiency. In addition, as a rule of thumb, for every 10-degree rise in the temperature of the windings, the life expectancy of the insulation on the windings is reduced by half. So having a hotter machine both reduces the efficiency, but it also reduces the life expectancy of the motor.
Wow, this is remarkable. So not only we are reducing the efficiency if we operate at high temperatures, we're also reducing the lifespan of the motor, so it's not going to live for that long.
Yeah, exactly. And it's not just the winding that we have to bear in mind. The magnets inside the machine also perform differently at different temperatures. So it's important to know what temperature exactly we expect to have inside the motor. If the temperatures are too great, we also run the risk of irreversibly demagnetizing all the magnets within the motor.
Wow, so when looking at the magnets, once you have figured out the temperatures you're operating in, you may need to go back to designing the electromagnetics of you. Does that impact the electromagnetics?
Yeah, absolutely. That's why it's very important that you undertake thermal design at the same time or in parallel with the electromagnetic design and the mechanical design. The choices you make will impact, for example, the materials you select, the configuration of the slots and the number of magnets you have inside the machine. If your thermal simulations predict that the magnet is too hot, you may need to reconfigure how exactly your machine is designed. In order to then move the losses from the magnets to the windings, which might be better cooled in the machine. So if the thermal simulations are an afterthought, it might not be possible to obtain the motor you expect, or your machine insulation might fail, and you'll be left with a costly problem.
Wow, this problem is definitely more complex than I initially thought. Like, there's so many things to take into account, and I'm very glad that we have tools to be able to systematically analyze this. I also wanted to ask you, what are the most popular cooling solutions given all this complexity?
Well, there's lots of different cooling systems available, some more popular than others, and typically it depends on the performance you're trying to extract from the machine, any cost considerations, and also any integration with other cooling systems present where the machine is finally deployed. So a common and low-cost solution, which you might see in industry, is just to have a fan-cool machine. So you'll have a fan mounted on the end of the shaft, and we blow air over the housing of the machine. And this is called a blown-over cooling system in Motorcad. It's easy to manufacture, it's reliable, but it has low effectiveness, as our cooling medium is far from the hot components inside the machine. If instead we allow the air to be pulled inside the machine and flow around the components and then be exhausted, This is we're bringing our fluid closer to the hotter components, so this provides enhanced heat transfer. In MotorCAD, we call this the through ventilation cooling system, which you can see in the list of cooling systems in the MotorCAD screenshot. So to enable the cooling systems in MotorCAD is very easy. We simply go to the cooling tab and we choose the cooling systems we want to enable, and you can enable them in parallel as well. And then you set up the flow rates and the fluid properties, etc., that you require. Alongside those simpler cooling systems, we might have a more complex cooling system like a jacketed cooling system. In this, the housing has channels through which fluid flows. That can be seen in the images on the bottom of the slide here. In a typical automotive application, this fluid would be shared with other powertrain components, and so for this kind of system, maybe a system level design might be important to consider. There's also very high performance cooling systems, so oil cooling systems or slot water jacket cooling systems that we call them in MotorCAD. In these cases, we have the fluid directly impinging or in contact with the windings, the magnets, and flowing through the slot. It's quite a high performance and costly cooling system design, but it's becoming increasingly common for attractive automotive applications.
Thanks for showing us all this variety of cooling solutions that exist and strategies and designs. I really like how, depending on how much you're ready to invest in your design, and you can cool either like in a general way from the exterior of the motor, or you can go inside the motor and cool specific components inside the motor that really need cooling in your design.
Absolutely. And I guess one of the things I haven't discussed are constraints such as the volume of the machine or the weight of the machine. Those are all very important, as some of the cooling systems result in more compact machines, whereas say an air-cooled machine might have to be larger and have a larger housing to allow the same amount of cooling performance.
Definitely. And it's great that MotorCAD includes models for all those cooling strategies. I particularly like the fact that you can combine multiple cooling systems and analyze transient responses. I imagine the coolant inlets and outlets are often, as you described, part of a larger system. For example, let's consider an electric vehicle. Here we have two motors, which has been the focus so far of the cooling for us. But there's also battery packs, chargers, DC-DC converters, DC-AC converters, lots of components that need also cooling. And there can be opportunities to integrate all of these systems together and optimize from a holistic perspective.
Yeah, that's right. So the MotorCAD model focuses on the thermal performance of simply the electric machine, but many of our users then want to use this detail model and integrate it into the larger system, such as what you're showing here. So that the larger system which contains the motor, but also the power electronics and the battery pack. And then the cooling of the motor is then integrated with the coolant, flowing through all of these different elements, and that can be done in a smart way that improves the overall system efficiency.
That's great. And a typical platform where people can integrate models and design the full systems is Simulink and Simscape. This is a Simulink model of an electric vehicle, and Simscape can be used for also multi-body simulation. So it's a multi-physics, multi-body platform that supports iterative modeling. So another thing I wanted to ask you is, how can you export a thermal model from MotorCAD into Simulink and Simscape?
There's a few different strategies to export the MotorCAD thermal model. The simplest way of doing it, and one that's existed for quite some time, is to simply export the MotorCAD thermal matrices into Simulink, and that is a simple export at a fixed operating point, a fixed flow rate, and fixed inlet temperature. The problems with this is that it's only truly valid at the single operating point that you chose during the export. So if you change the coolant flow rate, if you change the coolant inlet temperature, if you change the speed, then the model is no longer truly valid. So you'll have some deviations from the real machine behavior. Another strategy that can be used to export the MotorCAD thermal model is to use the MotorCAD FMU. Effectively, the way it works is that Simulink will use the FMU to directly open MotorCAD and run the thermal model in MotorCAD and then transfer the results back into Simulink. And it will do this at each time step. As you can imagine, that's a much more accurate solution because it's using the physics built into the MotorCAD thermal solver. But because it's calling MotorCAD at every time step, it means that it takes a lot longer to execute. And it also requires a license of MotorCAD to run this.
Is there any alternative to this simple export that's only valid as a single operating point, or the co-simulation of MotorCAD and Simulink with FMU that takes a long time to run?
Yes, there is. There's a third option, and that's the option that we're talking about today, and we'll give a demo of. That is the MotorCAD thermal model import into Simulink and Simscape. This effectively takes the best of both worlds. So it has the speed of the MotorCAD Simulink export, but it also has increased accuracy, much like the FMU does. The way this works is that instead of the user choosing a single speed, flow rate, and temperature, they're allowed to select from a range of these values, and MotorCAD will then export the thermal resistance network at each of these different operating points. Simulink will then take these thermal resistance matrices and then automatically interpolate between them depending on what the user selects as the inlet temperature or the flow rate or the shaft speed. What this means is that the model is now valid over a whole range of different operating points, and duty cycles and system integration can be done with the resulting model without losing any accuracy that you might have otherwise.
Thanks, Hussein, for sharing with us all the different ways we can export models from MotorCAD into Simulink. For the rest of the webinar, let's focus on the latest export technique that is what we think also the most valuable for you, that consists of this repository that you can find in the internet if you just Google it. And then you can just click here in download, and you'll have all the files, all the MATLAB files and Simulink files that you need for performing the export. So once you have downloaded it, you can open this project file, and it will open 3 live scripts for you: generate, validate, and use Simulink thermal model. We're going to cover them 3 in this webinar, and let's start with the first one. So in the first one, you can here specify the MotorCAD file that you want to use for export. So we have chosen the E8 template for this webinar, and we're going to cover it from the beginning to the end, all the export and validation. But bear in mind that you can do the exact same process for your own motor, and it should work. So it's a very flexible way to do the export. So once you run this first part, it will open your motor file, and here's what it looks like. Hussein, what do you think about this motor? Can you comment a bit on it?
Yeah, of course. So the E8 template is an interior permanent magnet synchronous motor. It's rated at 80 kilowatts and it has a maximum speed of 10,000 RPM. So this particular design is based on an automotive traction motor, and it has a distinctive design with 2 layers of magnets and various ducts within the rotor structure, you can see. The cooling configuration for this machine is, as we can see, a housing water jacket, which is the dark blue material on the top and bottom of the machine through which fluid is flowing, and also internal air cooling. So the ventilated cooling system is enabled, which are the lighter blue arrows flowing into the machine from the right-hand side through the rotor structure and through the air gap, and being exhausted out of the left-hand side of the machine. These cooling systems can be enabled by going to the input data cooling system. So here we can see the through ventilated and the housing water jacket cooling systems are both enabled. And to set the flow rates and inlet temperatures of those, it's very simple. We simply go to the appropriate cooling system tab, in this case, housing water jacket. We set a fluid volume flow rate here of 5 liters per minute, an inlet temperature that we want. And then MotorCAD will then use that inlet temperature and flow rate in the calculations. The same also applies for the through ventilation tab. In this case, we can see here a higher volume flow rate of 500 liters per minute because we are using air, and a slightly higher inlet temperature of 40 degrees, which represents the higher temperature surroundings of the machine.
Great, thanks very much for this exploration of the motor cooling systems. So once we have run these two lines and MotorCAD has been loaded and connected to MATLAB using our interface included in this project, we can then select here the ambient temperature that we want to use for this export, and then also the operating points that we want to include in this export. So these are the speeds. In this case, we have three speeds here, 500, 3000, and 7000 RPM of the shaft. And then we have flow rate and inlet temperature for each of the cooling systems. As Hussein described before, we have the housing water jacket and ventilation. So we need to give all these dimensions.
So what are the kind of guidelines, Angel, for users to choose how many breakpoints should they choose, and how many combinations of calculations will MATLAB Simulink run?
That's a good question, Hussein. So the rule of thumb is the more breakpoints you add here, the more accurate your reduced order model will be, because the interpolations fitting better the non-linearities between each dimension. Mm-hmm. And so the problem is the more breakpoints you add, the longer it's going to take to run the export, because the total number of operating points is going to be larger. So if we start adding many points here, I think in this case, if you multiply the number of points in each dimension, we have 108 operating points. But as we add more points, it quickly goes up. So it's a trade-off between how quickly you want to get your reduced order model and how accurate you want your reduced order model to be between breakpoints. Because at the exact breakpoints, you're going to get the best results, because we're not interpolating in between.
Okay, thanks for that explanation, Angel. So how long will it take to actually run this on a computer?
In this case, with these breakpoints, it takes about 15 minutes in my computer to run. So it's not that long. Yeah, so let's run this. Great, so after 15 minutes of calculations, this model has been created for you. It has our reduced order model and certain inputs that are configured as constants for us to quickly test it. So I'm going to click run while I comment a little bit on the inputs. So the inputs are the shaft torque and speed. And then we also have the housing water jacket and ventilated inlet conditions. So in terms of flow rate and inlet temperature. You can see here we predicted the node temperatures for 1000 seconds of simulation. And yeah, these are the results.
Wow, Angel, that was very quick to generate those results. So when you ran this simulation, did it require MotorCAD to run in the background, or are we now free from using MotorCAD?
That's a very good question. So actually, no. Once we have run this script that generates the model, this model is completely standalone. You only need Simulink to run it, MATLAB and Simulink. And all the data that has been generated through MotorCAD calculations has been stored in this model as arrays. And you can find all the values from the export here. So once you have exported the model, you can close MotorCAD and you can also share it with your colleagues, and you can directly use it here with MATLAB and Simulink.
Great. And what are the other outputs available to the user?
So we can also see the power, the heat flow in each node in this output. And we can also see the outlet temperature. So this is for the housing water jacket and for the ventilation, so that we can quickly understand how our fluid is warming up as it goes through the motor. And also, let me quickly show you how you can use this model not only for constant inputs like we do here, but I'm going to add like a constant plus a ramp in torque. So imagine like this is an automotive traction motor, as you said, and your driver is pressing the pedal more and more slowly to request more torque. Put like 0.1. I'm going to add a scope here to show what the torque value is. Let's run this again. So we're asking a torque that goes from 20 to 120 Newton meters, and we can see how our temperatures are increasing faster and faster since we are requesting more torque and current to the motor. Now that we have generated the model, people might wonder, how can they validate the model? How can they ensure that its results match MotorCAD's results? So for that, we can use this script called validate Simulink thermal model, where it will perform a transient calculation in MotorCAD, and it will compare it to the same simulation in Simulink. So the particular point we're going to study here to compare is a constant torque of 70 Newton meter, and then we're going to also select here which breakpoints we're testing in the table. So here's the third speed, so 7,000 RPM, and the second flow rate, etc. Yeah, I think it just finished. Here we have the results. Let's have a quick look. So we can see in blue is the Simulink results, and in red is the MotorCAD transient results. But we can see they generally match quite well. There's a slight difference for certain nodes of about 2 degrees. And here we can see the exact operating conditions. We are running this test for 7,000 RPMs, 10 liter per minute for the housing water jacket, 10 liter per minute for the ventilation, etc.
I think overall, what's the temperature range there? From 65 to 25 degrees, 2-degree temperature difference. It's not so bad.
Yeah, here it computes the maximum difference between the two for all points, and it's about 1.8 degrees is the maximum error that we're getting. We could do better if the loss maps here. So yeah, I'm going to quickly go through how the model looks like from the inside. So we have several modules here. There's the loss maps from MotorCAD Lab that compute for a given torque and speed. They will compute the losses for each type, which are the losses that the MotorCAD thermal model has here in this column, this table here. So it's figuring out the loss for each type. And then this module here, this subsystem, the power loss distributor, is going to figure out how these losses distribute into the nodes inside the motor. So once we have this array of node losses, in this case, I think we have around 123 nodes. So this vector has a size of 123 and is passed to the interpolated state space thermal model, which is all the collections of states of thermal matrices, state space model that MotorCAD exported. They're all put together here, stored in this state space ND array, and it interpolates the state space models based on speed, flow rate, and temperature, and also injects the losses at the nodes with this value here. That's the architecture of the reduced order model. And we have here temperature feedback to the copper losses that is applied in the power loss distributor subsystem.
So all of that thermal matrix knowledge is built into the interpolated state space thermal model block. And also the power loss distributor also has knowledge in terms of how the power is distributed over the different nodes, right?
That's right, and all of that knowledge is transferred from MotorCAD into this model, stored into these variables here that are also saved into the model workspace here.
Oh, great. But if I wanted to use different losses in this machine. If I didn't want to use the loss maps from Motorcad Lab, could I just remove that block and add my own?
Absolutely. So if you have a way to figure out loss for each type that is custom to you, for example, you don't have torque and speed as inputs, but you have D-axis current, Q-axis current as inputs, and you have exported from Motorcad a different way other than the labs with torque and speed, you could totally just delete this subsystem here and replace it with your version of the lookup tables and place it here. As long as you pass the loss of each type to the power loss distributor subsystem, then your model should be fine.
Oh, great. That seems very flexible. And I guess people who are familiar with Motorcad will know the losses of each type necessary to input for a particular model.
That sounds great. Right, so let's move on to how we can use this model now that we passed it to Simulink, how we can integrate it with other systems. So we have this use Simulink thermal model script that is, it covers a little bit of the architecture of the model that I already showed. So one thing we can do once we have exported the model is to do a drive cycle study. So we're going to have a drive cycle of vehicle speed and a simple model of vehicle dynamics that takes from a reference vehicle speed, what is the torque and rotor speed that we need. And we just put this with the generated model. And here we're also playing with some dynamic changes in operating conditions, like housing water jacket flow rate changing as a step, and the inlet temperature of the housing water jacket ramping up as it's running. We're imagining it runs as a cycle, like the outlet of the housing water jacket fluid comes eventually back in as in the inlet, so it's continuously heating. And we're going to try to mimic a little bit all of that and see how we can get some insights about the temperature in different components inside the motor. So here we're running a 2000-second simulation. And since we have now more dynamically changing inputs, the model takes a bit longer to run, but it's still significantly faster than real time. So you can see how we've already simulated 260 seconds in time it took me to say this sentence. So it's still useful at this rate. And I'm going to stop it here, but you can run it and then answer certain questions like, okay, in this drive cycle, what is the maximum temperature we get for the magnets or the copper? Are we at risk of breaking up the insulation or demagnetizing the motor? So this comes back to the observations Hussein did earlier about what is this useful for, right?
Thanks very much for that demo, Ankel. I think it really showed how easy it is to both export the model and also then use the model with varying drive cycles and how simple that can be to set up.
I'm glad you think it's useful. And another model that I wanted to show you is how you could then integrate this motor cooling, motor thermal model into a bigger system that has other components that also either need cooling or provide coolant. And so we typically use Simscape when we want to model multi-component, multi-physics systems. And in this case, we have our motor that has a housing water jacket inlet and outlet, which is then driven by a pump that is driving the water in the motor and through a radiator that will dissipate the heat to the ambient. And then on the other side, we have inlet and outlet for the ventilation, which is air. So this here is a thermal liquid domain. It's a liquid that can change in temperature. And but here we have a gas domain. So we have air that also can enter here and then come out hotter from the motor. And in this case, it's being driven by a fan, which is driving here at a constant speed of 1000 RPM. Then we also have a vehicle dynamics to kind of how the motor would then provide torque for a car, for example. And we have a driver model here in Simulink, which is trying to track So there's just a PID controller, which represents a driver trying to request a torque from the motor that will make the speed match the reference speed. So we have, again, a drive cycle here. I'm going to click run. So you can see how once you have integrated your model into the bigger system, you could then find out opportunities for trade-offs with other components and also helping other teams working on this cooling system to provide to find the specifications and performance, measure the performance. Again, since this model contains more components and it's more rich in behavior, it will take a bit longer to run than the others, but it's still a reasonable, around a bit faster than real time, so that it can still provide you insights fast enough for you to improve your design.
So in this case, it's not just the fixed analysis that you might do in MotorCAD with a fixed flow rate and temperature, but here you're incorporating the real physics of the radiator, the fan, and I guess you said these results would generally be shared with other team members and be used for their design as well.
That's right. Yeah, you could share models and have people replace components with their own models so that they can evaluate how their iterations in design have impacts on the other team's requirements and performance. So it's a great way to collaborate. Like there could be a team working on designing the radiator, another team working on the vehicle dynamics or like the driving style of the user, and you could figure out how all these things impact each other in this kind of collaborative model.
Amazing. And within that main block of the MotorCAD model, were there a lot of changes you needed to make to set this up, or was that fairly simple to do so?
I'm glad you asked this question. I wanted to show you that. So if you look at it, we have the original reduced order model subsystem that MotorCAD, like we generated before, and we just put it here, and we just put some adapters here, shaft interface, ventilation interface, and housing water jacket interface, and we connect it in a loop. So we connect the outlet temperatures that are calculated from the reduced order model. We pass it to each of the cooling interfaces, and then the cooling interfaces figure out the inlet conditions and pass it to the MotorCAD. And running this in the loop then works.
So it's kind of a little trick there to use the outlets of the reduced order model temperatures as the inlets of the cooling systems.
Exactly. It's a little modeling trick, and yeah, then you can integrate this in a SimScape model, so it can be useful.
And is all of this available for our customers to access and to modify directly, or will they have to set all of this up themselves?
This is available. They need to run the export for their own motor, and once they have the Simulink subsystem that has been generated for them, they just delete this one and replace it with their system, and they can test it in this particular condition. I guess for bigger motors, you may need bigger radiators, so you can come here and modify your radiator model so that it can radiate more heat. But with some modifications, you could then see how this you can integrate it in SimScape. For example, we have certain examples of electric vehicle cooling systems, and you can see here we have a SimScape model similar to what we had before, but with many more components. It's a more complicated one. But you can come here and in the same way I described before, you can place your motor here and then observe how it impacts in the cooling of the inverter, charger, battery, etc. And you can then rearrange everything to your particular vehicle design and have everything modified. But yeah, this would be how you can integrate it into SimScape models.
Great, thanks for that, Ankel. I think very comprehensive, and there's lots of different pre-existing templates already available for our customers.
Great. So it's time to bring this webinar into conclusion. And I wanted to ask you, Hussein, what do you think are the takeaways that we should leave this webinar with?
Oh, thanks, Ankel. Well, we've shown that the thermal design of electric motors is critical to the machine performance, and it's also a non-trivial. It needs to be done at the early stage alongside electromagnetic analysis and needs to be comprehensive. We've also shown how there's several different cooling strategies available depending on the parameters and the machine performance you are trying to extract. And overall, depending on the strategy you choose, the continuous performance of the machine will be determined. We've also shown how simply by doing component level analysis is not enough. We can get good results, but we are not getting a full overview of how the machine would behave in a real system. So the integration of the components into system models allows for this holistic design, and also then optimization of the individual components, optimization of the whole system as well. So we achieve a final better design. And finally, we've shown you a new automated MotorCAD thermal model import to Simulink, which is available to you today to download from the MathWorks website, which allows you to take the MotorCAD model and integrate it into a system model easily, effectively, and with accuracy.
That's right. And we invite you all viewers to download this repository and try it out with your own machine designs. And please let us know what do you think.
Yep, thank you so much for your time today, Ankel. It was really great to collaborate with you on this.
My pleasure. It was a privilege to work with you on this. Looking forward for more collaborations and for the feedback from our viewers.
Absolutely. Take care.
Take care. Bye.
Bye.